We derived the shallow water equations and some wind-driven circulations and so on for the ocean, but the atmosphere turns out to be very difficult, especially when you want to look at the meridional circulation that is going all the way from the tropics into the polar latitudes because of all the instabilities and the transient and stationary eddies involved, and the coupling between the momentum transport, heat transport, and the circulation. So we end up with what are called thermally direct cells and thermally indirect cells and so on. So we will kind of pass through them here without deriving the equations, because the derivation of the equations is quite hairy, but it is done very nicely, and in fact the physics of it and the math of it is incredibly cute. So Holton's book is the best for that, and there is some new version by Holton and somebody that is published recently, but you can stick to the older Holton, which has beautiful derivations. The book, Tom Stoker's book, doesn't explain the scale height and the derivation of the pressure coordinate, so let me do that, geopotential height and so on. So let me run through that here from the John Marshall Alan Plum book, which I use for my dynamics course, which is available on my channel as well. So dpdz is minus rho g from our hydrostatic balance. We can, for the atmosphere, write it as minus gp or rt, because ideal gas law, rho equals p equals rho rt. So we just replace that. Then we can invert this and write dz dp equal minus rt or gp, and then we can write that as p times d partial p equal to partial ln p. I think you know how to do this math. Whenever you have 1 over p and dt dp, you end up with exponential or ln p. I don't know, I'm fumbling it. Okay, so then you can write dz dln p equal minus rt over g, because we have taken p on this side and included in here. And this is called a scale height, where basically it's the height at which temperature drops by 1 exponential. So if you started from the surface within a scale height h, the temperature will decrease by 1 exponential. That's the definition of a scale height. So this simply gives us a relation for pressure as a function of height equal to ps times exponential minus z over h, where h is the scale height. So pressure here drops off by 1 exponential by the time you reach 1 scale height. And you can invert this and write z or z equal to scale height times natural log of ps over p. So you can easily flip between z as the vertical coordinate or pressure as the vertical coordinate. They are intimately related through this relation. In the low latitudes they tend to be almost the same, but we can use this relation to also define the so-called geopotential height. So if the temperature is not constant, here if you assume temperature equal to constant, you end up with that relation. We didn't let T vary with Z, but in general temperature of course is a very strong function of height, so you can assume that scale height is a function of height z as well, so that is rtz over g, but in general you can take the average average appropriately chosen average temperature, and that will show you that this h and this h are almost the same, but let's not digress in that direction. So writing again dz dp equal to minus rt or gp, zp zp here can here directly be written as r times integral, so we take the negative sign inside by flipping the direction of integration from p to ps instead of ps to p, times t divided by g dp or p. So this is just saying that the height of any pressure surface is a function of the temperature below that. So if you integrate this relation, this function from the surface to some p, then that height of that P is determined by how warm the temperatures are below that. This is what we already saw when we saw the temperature distribution in the zonal mean meridional. We said the tropical temperatures are warmer at all altitudes compared to the higher latitudes, because warm temperature expands the atmosphere and the surface is lower at the same altitude compared to the higher latitude. Okay, that's a very simple relation. So you can set z at ps equal to 0, and that allows you to write height as a function of pressure, which is what we call the geopotential height. Okay, so this is the relation, and you can also compute the tilt of a pressure surface from it. So if you take a latitudinal temperature difference of delta T from warm to cold, you know what the delta T is, and using this relation you can approximate the slope in the pressure surface delta Z, which is what we looked at before when we said the pressure gradient increases with height because the tropics are warmer and warmer compared to the high latitudes at each height. Okay, so those are simple relations to keep in mind before we move to this simple depiction of the Hadley circulation by George Hadley way back in the 1700s. He was smart enough. He realized that angular momentum conservation on the rotating planet is important. So he proposed that in the deep tropics there is heating. Air rises, gets lighter and rises and hits the upper atmosphere and has to go towards the poles, and then he said it is will be forced to sink, and he assumed that, and he knew that angular momentum has to be conserved. So he proposed that the air parcel that is rising is taking the angular momentum in the low latitudes, which is very high as we just saw, and it will keep getting tilted more and more eastward as it goes to higher latitudes, because the earth below is moving slower and slower. So he got the jet stream in that sense. So V is greater than 0 because the air is forced to move towards the poles. U is greater than 0, which means the winds are going from west to east, which we call westerlies. So you end up with a jet stream, and the air sinks and has to come back towards the tropics. And here he assumed again that you are bringing momentum, angular momentum from here, which makes you lag the earth, which is moving faster and faster, which would make you tilt. So the zonal velocities then become negative, which gives us easterly winds in the low latitudes. Of course, trade winds are northeasterly and southeasterly converging into the ITCZ, but he explained all the essential features of the meridional circulation. He was of course partly wrong, because the cell doesn't go all the way to the pole and come back. It has to terminate somewhere in between, and there are obviously dynamic reasons why that happens. And so because of that, the cell is now called the Hadley circulation. Okay, to do this mathematically, we have to go back to what we did before in terms of finding the mean or spatial and temporal mean of transport terms, typically like A times B, where we had written them as A bar plus A prime plus A star, where we had written stationary eddies and transient eddies. So we took the time average and the spatial average and split it into multiplication of the time and spatial averages plus the transient terms, the eddy terms that go to 0, and the stationary eddy term that doesn't go to 0, and the transient eddy term that doesn't go to 0, which we wrote as this. As an example, when we look for meridional transport of heat, we look at V bar T bar of the spatial average of V times T bar, which ended up giving us the transport, meridional transport by the mean flow. So V bar stationary average, T bar spatial average, sorry, plus stationary eddy contribution and a transient eddy contribution. If the correlation between them is not zero, then obviously they contribute. So for the angular momentum here, for the meridional circulation, we do the same thing. Zonal mean meridional V times L, the angular momentum averaged in time and averaged in space, gives us the V bar square bracket term with omega r cosine phi plus U bar spatial average times r cosine phi, which is the mean angular momentum transport, plus you get a stationary eddy contribution and a transient eddy contribution at any latitude phi. Okay, we didn't do any magic. It's exactly the same derivation which you can do by using the expression for L that we wrote before. Without going through the derivation, we again do the zonal averaging to look for meridional mean terms. So we take rho 0 as a density profile that only varies in the vertical. So rho 0 is a function of height, and we get the meridional momentum term to be some stream function that basically gives us the vertical profile, and obviously the meridional circulation is tangential to that, so minus del chi bar del z, and we want to plot vertical meridional circulation, which is what we looked at before, right? When we looked at zonal mean meridional section with height, we are basically writing vertical meridional equations. So rho 0 w bar then can be written as del x bar del y. Why can we write a stream function? Because when you do zonal mean meridional, it has to be non-divergent, right? So you can easily assume some sinusoidal function to satisfy boundary conditions, but basically the equation without deriving it for the meridional circulation becomes a complicated looking thing like this, which is a form of the Poisson equation that we looked at before. So you have del squared form here with some forcing terms on this side. So you have n squared over rho 0 del squared chi del y squared plus f0 squared del z of 1 over rho 0 del chi bar del z. Rho 0 is a function of z, so we have to keep it inside, and this is derived in Holton, so you can look up, but we will just look at the terms here. This is equal to kappa divided by h, the scale height, times del j bar del y, which is the diabatic heating term here. N is the Brunt-Väisälä frequency. N squared is given by r star over h times kappa t0 over h plus the lapse rate dt0 dz. So kappa here is r star over cp. R is the universal gas constant for air. H is our scale height that I just showed, r star t tilde 0 over g for t0 equal to t0 z. So this is the average over the scale height, and z is given by minus h ln p over ps, the geopotential that we had defined, and x bar here is a mean drag in the zonal direction by friction. So this is the friction term. So the balance of the meridional vertical circulation is accomplished by the diabatic heating term that we looked at the rainfall distribution and talked about it, the transient eddy heat flux term, and the transient eddy momentum term. So amazingly here, the meridional circulation, the temperature transport, and the momentum transport have become coupled because of the way the atmosphere is driven by the heating. So chi bar then here is essentially a balance of the meridional gradient of the diabatic heat sources with heating, strong convection heating in the deep tropics, plus the second derivative of the meridional eddy heat flux term that we looked at here. Similarly, d squared dz dy of the meridional eddy momentum flux that we saw here, and the zonal shear or the drag, which is basically the energy dissipation along the way. So at mid latitudes, minus f del x bar del z is 0, so there is a drag at the surface. But looking at the large scale balance, maybe I should do this in the next podcast because I already put in too many things into this equation. So let me stop here and we will come back and look at the balance of terms in the zonal mean meridional sense so that we can give it proper time to understand the balance of terms and how they change in the meridional direction and why we get the thermally direct cell like the Hadley cell and the thermally indirect cell like the Ferrel cell. Okay.